We'll introduce the next speaker. So speaking to us today about experimental and statistical fracture pattern analysis of glasses with varying pre-stress levels. So we have Leon Bohmann here next to me from Darmstadt University, if I pronounced that right.
Yeah.
So the floor is yours.
Yeah, thank you very much for the kind introduction here. We've talked a lot about glass and the post-fracture states today, as you heard maybe also yesterday from Lina Efforts. The post-fracture states are becoming very important. It's both for the German standard and for the upcoming Eurocode. And that's why today I will focus on the post-fracture behavior based on the fragmentation of individual glass plates, because that is the first step to understand how the laminates will behave upon fracture. So here, maybe you can start the left video. Here I want to show the fracture of glass with two high-speed images made with 5 million frames per second. And as you can see, for low pre-stress levels, we have pretty easy to understand fracture patterns that are created during the process of fragmentation. However, if you would start the second video, please. If we increase the pre-stress level and also the thickness, giving us a lot higher initial strain energy, you see that the fracture process gets very tedious. So we cannot really see which one of these cracks is a primary crack, a secondary crack, or which orientation do these cracks actually have, because some of them are also have a really three-dimensional fracture path through the glass plate. So now I have to cycle through them. So yeah, to conclude these two videos, we can see that the heat strengthened glass gives us very nice looking fracture patterns, while the fully toughened glass gives us almost the homogeneous fracture pattern here. What we can conclude from that is that the initial strain energy that we put into the glass by pre-stressing it is a large factor to the fracture pattern that is created after the fracture stopped. So what the task is for me, or is to find a method that can generate these patterns, because I didn't want to bother myself with the implementation or the process of fracture itself. So the idea is to look at the boundary conditions that we have before fracture, then look at the fracture pattern that was created using these boundaries, so the pre-stress level, the boundary, the support condition, the dimensions, and then find a way to stochastically determine the post-fracture pattern. Yeah, so we're not modeling the fracture process, we're just looking at how does the pre-stress level, for example, influence the fracture pattern. So to analyze the fracture patterns themselves, we have to identify features that are interesting for us and are important for the fracture pattern as a whole. So the two main features that are to be identified is, first of all, the geometry of fragments, which is called the first order stochastical measure, because we are looking at how does one single fragment look like. For example, what we can do is we can look at a single fragment in here and try to describe how does it look like. It's rectangular, it has a certain circumference, it has a certain area, and also it has a certain orientation towards the fracture origin. I will show you an image of that one or two slides later. The second one is called a second order stochastical measure, which looks at the relation between different fragments. For example, we can look in the region down here, and we see three larger fragments and one small fragment, and we can count that by using a so-called Lagrangian measure. But that's not really important for this talk, so I will just skip on to the next slide here. As I said, to describe the first order stochastical measurements of these fragments, we are fitting an ellipse onto the fragment itself. You can see that denoted here with the green ellipse, and in the background you see in red the fragment itself. By just measuring the pixels and applying a factor of the dimensions of the actual experimented glass plate and the image, we can then deduct the R1 and R2 axis lengths. The second order stochastical measure, the intensity that we can see here on the right, is, for example, measured by counting individual fragments and then dividing that number simply by the area that has been taken by these fragments. And then we get the so-called fracture intensity. Now, the problem is, or the main consideration that has to be taken into account here, is that these measures and features differ when we look at different positions on our fracture pattern. What we can see here is a fracture, is a specimen of a height of 500 millimeters and the width of 500 millimeters. The fracture origin is at the top left, and now we are looking at certain windows over this fracture pattern. If you look very closely to the fracture pattern, to the fracture origin, we can see that the individual geometries of the fragments are differing a lot. We have some smaller fragments, we have some longer fragments here or down there, but as you can see, the orientation is pretty much, everything is pointing into the upper left corner, so just where the fracture origin was. However, if we then go further away from the impact position, we can see that there aren't any more that many long splinters, fragments such as this one, pointing into the direction, but we get a more random-looking fracture pattern. Then, almost in the middle, we can see a very homogeneous fracture pattern. We don't have any orientation left. And now, going further away, at the furthest position away from the fracture origin, we can see that it's still looking pretty random. So, what does that mean for our analysis of the fracture pattern itself? We have to take into account the distance from the origin. So, the distance from an individual fragment here from or in other words, the geometry of such a fragment is highly dependent on the distance to the fracture origin in the top left corner. So, to do these kind of analyses then, we are dividing our fracture pattern into radial bands, originating in the fracture origin on the top left. In each of these radial bands, we can then come up with a representation or an average of any feature that we like from the geometry. For example, the circumference, the intensity, the orientation, whatsoever. To do that, and to find these features in fracture patterns, we do have to do a lot of experiments. That's what I did. So there are, in our project that we're doing, are 750 experiments to be conducted, and I've already done 250 of those, which are done as follows. We have, as I stated earlier, the 500 by 500 millimeter glass plate, and we are putting it into this contraption here. We close this contraption, and then it looks something like this. We have the glass plate that is laying inside here, and we have a fall weight of 2.4 kilograms, which we are dropping in this high-tech PVC pipe fall tower onto our glass plate. Once that's done, we're using a soft solution collet scanner, which scans the fracture images and gives us the scans that I've showed you before. So now that we did that, we have 250 fracture patterns, and each of these fracture patterns has to be analyzed using a Python script in these radial bands for the R1 value, so the larger ellipse axis length, the orientation, the intensity, and the mean average distance between two or more fragments. If we do that, I've brought an example here for the fracture intensity. We can see the colored bars is the energy per unit surface. The top graph shows the 8 millimeter thick glass plate, the bottom shows the 4 millimeter, and the y-axis gives the intensity, and on the x-axis is, you see, the distance to the fracture origin. And quite easily you can see that when we increase the energy from very low values to very high values, the influence of the distance to the fracture origin decreases. It gets smaller. Yeah, so we have these two dints down here, but if you look at the 8 millimeter glass plates, they are getting pretty small. And that's basically just due to the fact that the higher the energy, the less other influences are there that can create different fracture patterns. Yeah, so if we put a really high value of, let's say, for example, 160 megapascals of pre-stress on the surface into the glass, other factors such as inhomogeneities or anisotropy effect from the pre-stressing, they're getting negligible. If we do that now or we switch the representation here because that gets a little bit easier to read. So now we're switching the colored values of this matrix-like form into the fracture intensity, so the value or the feature that we want to analyze. We put that in this matrix form. Yeah, you can imagine that each of these pixels in here is stored in the matrix. And if we now want to, for example, look at a specific system with pre-stress surface value of 100 megapascals, we just have to look into this y-axis line, and then we can use this line to say stochastically how large is our fracture intensity at a distance of, let's say, for example, 250 millimeters from the impact position, and we can then use that value to create our fracture pattern. Now I see I've talked a lot more than I originally wanted to, but let's see if I can get this into this presentation. So now we have the intensity, and we are distributing these points again in radial bands around a thought of impact position in the center. Yeah, you can see that there's not a lot of intensity, then it gets a little bit higher, and then there's a little bit less intensity here, basically giving us the scalar function that I've talked about before. But these are only points. But the main goal is we want to have fracture patterns. Yeah. So there's one last thing, or a couple of last things that we need to do. And the first one of these things is we are applying so-called prototype geometries. We're just saying, okay, I'll say the base fragment in such a fracture pattern has an elliptic shape. That's wrong, of course, I know, but for a prototype, that's good enough. If you now imagine that this fracture pattern here has a lot of black, and black means I don't know what that is. All I know is that stochastically speaking, these ellipses have the right length and the right width of the fracture patterns I've analyzed before. So now we have to get rid of the black spots, and I see that please ignore these numbers, they are wrong. We have to distribute these black spots to the fragments that we know of certainly. And that's where comes the watershed algorithm into play. We have some unknown spaces around the fragments of the prototype geometries, and we are distributing them to the neighboring fragments here. And once we've done that with every single ellipsis on our 2D image, we get this. And as you can see, by pure eye, that looks, for me at least, pretty similar to a fracture pattern that was generated during an experiment. But the one on the left is based solely on artificially created stochastic properties that have been taken from a lot of experiments that have been conducted. So far, so good, looking good to the naked eye. But what I've also done is I've used this method to compare it to actual reference experiments. And as you can see, with the green line here depicting the method that I've just shown, we can see that the average value of the fragment base area is hit pretty good, and also the curvature is quite nicely. We can also capture some smaller fragments and even some larger fragments for the heat strengthened glass. If you're looking at the fully toughened glass, the curvature is hit even better. That's basically because of the reasons I've told you before, that the higher pre-stress levels lead to the negligibility of other factors. However, if we're looking at the circumference, and that's a little shortcoming of the method, the circumference gets larger, a lot larger, because on the bottom you can see that the x-axis is logarithmically scaled, so they are completely off. And why is that? Well, it's basically because of the watershed algorithm, because the circumference is not limited. We can make little dents in the fracture pattern that we created, and the circumference will get infinitely larger, while the fragment base area is somehow limited because there are only so many pixels that we can count. Another thing that I've looked at is if I now go on and use different geometries. So if I'm not using the square part 500 by 500 millimeters, but look into the standard values of 1100 by 360, you can see that the fragment base area's curvature is pretty well represented. Like here, you can see the peak is almost, it looks like it's shifted to the left. And there's a pretty easy explanation for that as well, which is that the calibration that we've done earlier has only been made to a certain distance to the impact position. And now that the glass plate itself has become larger, obviously there's no calibration, so we need to kind of extrapolate, and that's never a good idea to do in data-driven analysis. So I just want to give a small outlook at the end. So the features that I've identified in the fracture patterns before, that was done by me, by my eye, by my brain. But maybe there are some features that I didn't see, and that's where machine learning approaches might come into play, where we can look at the raw data and let the machine itself decide what is important for the fracture pattern. Who knows? Then there are different averaging techniques, and what I mean by that is I've shown you the matrix before with the colorful parts of the fracture intensity. They are interpolated linearly between two fracture states. But who knows, if we look at more dense data models, we need other averaging techniques, like we could do something non-linear. Then I've used the elliptic geometry, prototype geometry, but maybe that's also not the right choice for fracture patterns, because from previous literature we know that hexagonal shapes should be better. Then, as a last step, maybe there's some way to implement the physical properties, because we've skipped that now completely, but maybe it's a feasible way to somehow implement that into the method itself. I really thank you for being here. Thank you for joining me this late afternoon. And I hope I can see you in the farewell party. If you have any questions, just come ahead and feel free to ask. Thanks.